All right, here we go. More FRQs from old AP exams. This is year 2013, question number 3. This is a non-calculator question and also falls under the category of table of values. And the dead giveaway is at the very top. You see a table of values. So let's read the question and see what's going on here and get our mind wrapped around the context. So, hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t, 0 less than or equal to t less than or equal to 6, is given by a differentiable function c, where t is measured in minutes. Selected values of c of t measured in ounces are given in the table above. Alright, so it looks like we have a coffee cup under a coffee maker type of device, and as every minute goes by, the cup is filling up. And so that makes sense here on our table. There's the 6 minutes, and there's how much coffee's going in. This one seems fairly understandable and straightforward compared to how weird some other questions can be of this style. And so I want to revisit one little part here that you don't get confused to what C actually represents. So it says the amount of coffee in the cup at any given time is given by the function C. The reason I want to stress that is you should be thinking to yourself that C is actually a volume equation, because that's how much coffee is in the cup would be measured by volume. C is not a rate, and that's important to keep in mind. It's just volume in the cup. So how much water is dripping through the coffee maker filling up the cup? The amount of coffee in the cup, that's the function we're looking at. These are the selected values. So clearly at time equals 0, there's no coffee in the cup. And after 6 minutes, you've got 14.5 ounces in the cup. All right? So since we understand what's going on, let's use the strategy of sketching a graph here, because there's going to be a good chance we're going to have to approximate area under the curve using some sort of approximation method. And I'm going to make the horizontal axis as long as I can fit in here, and this will be time. And since we only have 6 units here, I'm going to make these x values fairly far apart, or t values. So there's 1, 2, 3, 4, 5, and 6. And then as time goes on, the amount of coffee in the cup is increasing. So when I get down to the end here, I'm just going to put in my top value here. That's going to be 14.5. And then I'm just going to keep decreasing here. So again, we don't worry too much about scale. That's not going to be that important. This is just kind of to give us an understanding of what's going on. So don't get too worried about that part. So there's 8.8, and there would be 5.3. So when time begins here, we're at 0, so 1 minute we're 1.53, 2 minutes 8.8, 3 minutes we're 11.2, 4 minutes we are 12.8, 5 minutes 13.8, and then 6 minutes 14.5. Alright, so we'll just sort of connect those, and that's what's going on. Now the problem says that the function is increasing the whole time. Okay, so it might look linear just the way I sketched it here, but doubtful. Don't make that assumption. It's just increasing the whole time. That's all you got to worry about. Okay, so now it says use the data in the table to approximate C prime of 3.5. Now hopefully by this point you're starting to almost, you can predict the question sometimes. It's asking us for a derivative. Well, we just graphed C. They want C prime. You know a derivative is the slope of a tangent. So since they're asking me to approximate or estimate, I'm going to have to find the slope of the secant. They're asking me for A rock. So as I look at this, I'm saying, well, they want C prime of 3.5. And this is where hopefully you're getting to the point where you're saying, well, what if this would have been position, velocity, acceleration? The derivative of v would be acceleration. Well, this is just, coffee in a cup. There's no special formulas here that you would know from other types of questions. But if in the cup is C, is volume, then C prime would be the rate the volume is changing. So here's the rate. Find the rate, approximate the rate the volume is changing at 3.5 minutes. Well, just like other questions, when they ask you to approximate, they always give you a value in the middle of an interval. Well, 3.5, I'm going to put that right here. there it is. They want you to approximate the slope of the tangent, which is the derivative right there. And so how do you approximate the slope of the tangent? You use the slope of the secant, so use the points on either side. Now in this particular graph, this looks so linear the way I drew it, everything's overlapping on itself. But you just go, oh, okay, I get the drill. I'm going to find a rock. I'm finding my average rate of change, and the interval I'm using is 3 to 4 to find out the in-between here. So I'm just going to say, all right, no problem. It looks like at point 3, I have 11.2 as my y value. And then I'm going to subtract from it 4, and the y value at 4 is 12.8. Now we should be getting a positive number here. So we get negative 1 on the bottom, and then we get 12.8 minus 11.2, and we should be getting 1.6. And that's negative. So negative over negative is positive. And so it looks like we get 1.6, and let's get our rates down, or our labels down correctly. This is in ounces, and so I'm going to say it's ounces, and here's where you got to be careful. Many times when we've been doing these questions, the time is the rate of a rate, and the time would be squared. Well, this actually is just the rate of volume, so I'm not squaring the time, it's just ounces per minute. Okay, now that could be a moment of pause for some of you to say, wait, why isn't it squared? And again, I'm finding the rate the volume is changing. I'm not finding the rate of a rate. If C would have represented a rate, then I would be taking time squared. But it isn't. C is not a rate. C is just coffee in the cup. Okay, let's move on to part B. Part B says, is there a time, t, in the interval 2 to 4, at which C prime of t, or the derivative, is equal to 2? Justify your answer. Well, let's do a brief time out here and do a review of a concept. So earlier in the year, I'm going to put some notes over here. Earlier in the year, you may recall, we had this diagram where we had a random function here we'll call f, and if this was a and this was b, we would say, what is the slope of the line connecting those 2 points? And that would make this y value f of a, and this y value f of b. And so this is a secant in the interval, and let's just calculate that volume here, or sorry, the slope. So we'd say, oh, well, the slope of the secant, here we go, back to algebra 1, the slope of the secant would be the difference in the y values, f of b minus f of a, all over b minus a. Okay, that's nothing special, that's just fancy notation for the slope of a line. Then we would say, is it possible that there is a point in the interval a to b such that the y value at that point is parallel to the secant? Or is there a value in the interval such that the y value, slope of its tangent or derivative, is equal to the slope of the secant? Another way to say it is there a time in the interval where the instantaneous rate of change is equal to the average rate of change? So if you guys look at this, and I'm just going to approximate, let's say it's right there. There's my tangent, everybody. And so this would be my c value, and this would be my f of c value right here. So, is there a time in the interval a to b such that the derivative at c, the slope of the tangent, is equal to the slope of the secant? I'm going to write that down here. So the question is there a time in the interval where the slope of the secant is equal to the slope of the tangent? And I'm going to write it a little more formally. F of b minus f of a over b minus a. That's the slope of the secant. Is there a time, is there a c value where f prime, or the derivative, is equal to that? So here's the slope of the tangent, here's the slope of the secant. The answer to the question is yes. And the reason is the mean value theorem. And that's what I just made here. Given a function that is continuous and differentiable over an interval, the mean value theorem says there exists a c value in the interval such that the derivative at the c value, or the slope of the tangent, is equal to the slope of the secant from the endpoints. Now, this becomes very handy in the type of question we just have, because what they're saying is there a time in the interval 2 to 4 where the derivative is equal to the slope of the secant? Well, what you guys don't know until you do this problem is that the slope of the secant is 2. So we're going to calculate that and show it. But this is actually a mean value theorem question. So they like to sneak that in sometimes on an FRQ, and if you haven't run into it for a while, it seems impossible, but then after you see it, you go, oh, that's what they're doing. They're being sneaky and sneaking in a mean value theorem question, and that, once again, is the value of doing old AP questions, is you start to see that, and you won't be surprised. So that is the context of this question. So now let's go back over here and say, is there a time in the interval where the derivative is equal to 2? Well, that's where, again, this 2 might seem really arbitrary, but you're going to see how it's not here in just a second. So let's find the slope of the secant over the interval. So what I'm going to do is I'm going to say, well, what is the slope of the secant from f of 2 to f of 4? All over 2 minus 4. There's the slope of the secant. So let's go to our table. So you can read that. That's a 4. Let's go to the table and put in these values. So from the table, f of 2 is 8.8. F of 4 is 12.8. And 2 minus 4, that would be negative 2. So what do we wind up with? We get negative 4 over negative 2, and sure enough, there's the 2. So that wasn't random that they said, is there a time where c prime of t is equal to 2? So that's where it came from. So now that we've shown that that's equal to 2, here's what we get to say. The answer is yes. By the mean value theorem, there exists, and so this says t, so we can say there exists a t value. There exists a t value such that f prime of t is equal to 2 in the interval 2 less than t less than 4. Okay, so our work up here showed that this was the slope of the secant, and so 2 being in that interval, that's the explanation. So 2 is the slope of the secant. So if we went over to our picture here, so you could say a would be 2, b would be 4, and the slope of the secant is 2, if you can imagine that. Is there a value in here where the derivative would equal to 2 in the interval? Yes, there was a time in there where it had to be by the mean value theorem. Okay, that is part B. Let's move on, part C. Part C says, use a midpoint sum with 3 subintervals of equal length indicated by the data above to approximate the value of 1/6 of the integral 0 to 6 c of t dt. Well, there's 2 parts to this question. Like, what the heck does this mean? Why is there a 1/6 out front? We'll deal with that in just a minute. But let's get the Riemann sum out of the way. And so this is the first time I think we've seen one where it says use a midpoint sum. Well, it's handy to use a midpoint sum because there's so many table values, and they said to only use 3. So since we're only using 3 intervals, we're going to go to the middle of our 3 intervals. So let's see if this makes sense. My 3 intervals, if I'm going from 0 to 6, my intervals have to go from 0 to 2, 2 to 4, and 4 to 6. So what I'm going to do is get rid of this 3.5 here. It's making my picture a little cluttered here. And I'm going to get rid of our mean value theorem. So I'll make a few notes here underneath. So what I want you guys to see is, here is our first rectangle. This will be our second rectangle. And this will be our third. So we're going to approximate there. But in the midpoint method, you're going to take the middle of the interval to be your height value. So I'm going to sketch this, and what you're going to see is that there's some area above and area below. I'm actually going to switch colors here for my rectangles. So here's what winds up happening. F of 1 is the height value we're going to use, because that's in between here. And so what I wind up doing is I say, well, I'm going to use this rectangle right here. That's the midpoint method here. And I say, I'm going to actually calculate, there's my rectangle. The width is 2, but the height is from the midpoint of the interval. Well, my next rectangle is going from 2 to 4. Well, the midpoint of that is 3. So this is how I'm going to get the height, and the width is from 2 to 4. Okay. And then the next interval is 4 to 6. The midpoint would be 5. So I think I want to make those dotted there. I think it'll be a little bit easier to understand. So the dotted line was the value that I used to get the height. Okay, and the solid lines are actually creating the rectangle. So this right here, okay, so those are my 3 rectangles. So using 3 intervals, it says use a midpoint sum with 3 intervals of equal length indicated by the data to approximate the value of this integral here, which we'll do in a second. So that's where that comes from. So whenever you do the midpoint method, you have to use the value in the middle of the interval, which was convenient for this one because the table of values was pretty robust there. So now it's just a little geometry from there. So let's see here. It looks like from this first one, the width is going to be 2 for each one, but my height was at 1. So it looks like triangle number 1 here is going to be, or rectangle number 1 is going to be 2 times 5.3. Plus my second rectangle here is going to be 2 times, and it's going to be the y value, or the height, actually the ounces of coffee in the cup at 3. And so from the table or from my graph here, that's going to be 11.2. And then plus our last one here is going to be 2 times the y value at 5, which would be 13.8. So again, you'll always find people that can do these types of table of values questions with no graph, but it's so much easier to understand when you can see what you're doing here. So I think, what do we get here? 10.6 plus 22.4 plus, is this 27.6? All right, and then we add these together, so 27 and 22, that's going to give us 49, and that's going to give us a 50. So I think we wind up with 60.6 right here. So that's what we get for our total here, 60.6. So if we take this value and we bring it over here to our integral, I'll keep it in red. It looks like it's going to be 1/6 of 60.6. And again, this is a non-calculator question, though you will have a 4-function calculator if you want. So if we do the division there, we're going to get 10.1, and what we're finding is, since we integrated the function here, we're going to get ounces. So it's going to be 10.1 ounces. Now, that's the first part of the question. So it says, use a midpoint sum 3 subintervals by the data to approximate the value of 1/6 of 0 to 6 ct dt. Using correct units, explain the meaning of it. Well, some of you might have noticed this little 1/6 is kind of a giveaway on it. And if you remember, this overlaps with, and hopefully you were able to guess this one, this is average value of a function. Average value of a function. And what they like to do, and again, you start noticing patterns, this part of the question, they're asking me about average value, and up here they were asking about average rate of change. They like to do that in the same question to see if you know your stuff. So if you recall, average value of a function is always equal to 1 over b minus a times the integral of a to b of whatever that function happens to be. Okay, that's average value of a function. So for this right here, what 10.1 is just part of the answer here, 10.1 ounces, and I'm going to just jump up here and write what that equals. And so it says, in the context of the problem, this is the average amount of coffee in the cup. From 0 less than or equal to t less than or equal to 6. Okay, so the average amount of coffee in the cup. I'm not sure if that seems intuitive or not, but it's a 14.5 ounce cup. What was the average amount of coffee in the cup in that time? 10.5 0.1, it's right in the middle there. I guess that seems reasonable, but that would be the average amount. Okay, let's move on. Part D. Part D says the amount of coffee in the cup in ounces is modeled by the function b of t is equal to 16 minus 16e to the negative 0.4t. So now they tell us, now that they've had us approximate everything, and they did this, and you're starting to notice they'll do that in the same question. They'll give you an approximation approach, and then they decide later in the question to say, well, now I'm going to actually give you the function. So that's what they did here. So now they say b of t is equal to 16 minus 16e to the negative 0.4t. Using this model, find the rate at which the amount of coffee in the cup is changing when t equals 5. Well, you guys have to get to the point where when you see that word rate, that's just got to jump off the paper at you. And this goes back to what's a derivative? Slope of a tangent. Be a little more specific. Formula for the slope of a tangent. What does it represent? Instantaneous rate of change. So they gave us C is the amount of coffee in the cup. They want to know the rate at which the coffee cup is changing. Well, that's just the derivative of this function. So this is actually a pretty easy question, but you have to understand the lingo. So they tell us that b of t is equal to 16 minus 16e to the negative 0.4t. And now do you know how to take your derivatives, because you have to know to take the derivative of an exponential here. And then we'll evaluate it at 5. Let's get b prime of t down first. So derivative of 16 is 0, and then we have the derivative of this exponential here with this coefficient out front. So we should say, well, that's just going to be negative 16, and remember the narcissist derivative here. So we've got e to the negative 0.4t, technically times the natural log of the base, but that's just 1 because it's e, times the derivative of the exponent. And the derivative of the exponent here is just negative 0.4. All right. So if you clean that up, and if you did 0.4 times 16, 4 times 16 is 64, but we have a decimal here, so it's 6.4. We have a negative times a negative is a positive. So if you clean this up, you wind up with 6.4e to the negative 0.4t. So that's what b prime of t is, and then they want us to figure out b prime at t equals 5. So we will say 6.4 e to the 5, or sorry, I think for some reason I wrote a 5 there. I was ahead of myself. That's a t. So now I'll put in the 5. So 5 times 0.4 is 2. So we would have negative 2. And this is acceptable to leave it like that, or if you want, you can bring this down to the bottom, and you could say 6.4 over e squared. And then we have our rate. It's a rate the coffee is changing. And so we would say, oh, well, that's just ounces per minute. And there it is. So again, from the top, we have a table of values that gives us how much coffee is in a cup. It's just volume. And we decide to graph it right here. The amount of coffee in the cup is increasing as time goes by in 6 minutes. Pretty straightforward. Then C prime, find the slope of a secant over an interval. Got it, 1.6 ounces per minute. Then a little bit odd with B. It's a little sneaky mean value theorem question, so make sure you have the mean value theorem reviewed. Okay. If you have to, just rewind and watch those little notes here we went over. And we showed that the answer was yes. And then down here, what does this mean? Once again, another somewhat obscure theorem here, average value of a function. And so we had that. So that's what the average value, that's what this equaled. We used our Riemann sum to get it. And the last one was just, can you take the derivative of an exponential? All right. So there it is, 2013, number 3, AP Calc AB. See you next time.